All right, so let's go back to the original question that I started this chapter with. What does this equation mean? Well, in the beginning of the chapter, we said this reaction refers to when you have one little FU of Cu2S and it encounters two molecules of oxygen, it will become two FUs of CuO and one molecule of SO2. But since then, we've realized we can't see that. How do we know that? We can't see that. That's too little. We can't see FUs, and we can't see molecules, and we can't see atoms. So instead of working with individual particles, we work with moles. Moles are enough of those particles. It's a unit amount of those particles that we can actually touch and feel and measure. So, does this make more sense? 1 mole of Cu2S plus 2 moles of O2 yield 2 moles of CuO and 1 mole of SO2. Does it make more sense? Yes, once you put numbers to this. You see, now we can determine the formula mass in grams. So if you add up Cu2S, it equals 159.2. Add up O2 and then multiply it by 2, that's 64. Add up 2 CuOs, that's 159.2 as well. Add up SO2, that's 64. Guess what? Both sides equal each other. Is that a coincidence? No. In chemistry, both sides have to equal each other. You cannot lose any mass in a chemical reaction, and you cannot gain any mass. That is the greatest, most powerful law of chemistry. The mass of the reactants must equal the mass of the products. Why? Because the atoms may rearrange themselves into new things, but the atoms themselves do not disappear. And the atoms themselves cannot be made to come into existence. Must equal. So that will allow you to answer the easiest question on every test from now on. Because I'm going to ask you something like this. 20 grams of oxygen plus 30 grams of hydrogen will equal how many grams of water? 20 plus 30 will equal how many grams of water? 50. It has to. It has to. The sum of the reactants must equal the sum of the products. They have to, because of the law of conservation of matter. All right, so with that preface, let's hit these two targets. This is actually getting really, really practical in chemistry, because most of the time chemistry takes place in water. In water. Okay? So, I have here black BLK, black water, that my Secret Santa gave me. Okay? Obviously, it's not pure water because it's black. Okay? That means there are things in here. There's dissolved things that are giving it its black color. Okay? How much? It doesn't say necessarily, but I bet you anything there are people who create this thing know exactly how much of the different ingredients are in there. One of the ways in which we have already learned how to determine how much stuff is contaminating another thing is by, remember, parts per 100, parts per million, parts per billion. Okay, that's the way the EPA measures how much mercury we have in our water. Do you realize that every time you take a gulp of water, you're probably drinking mercury?
Yeah.
And mercury will kill you. Why does the EPA allow mercury in our water? Because in teeny tiny itsy bitsy amounts, it's not going to hurt you. So they set limits for Oak Ridge, for Knox County, for Anderson County. Can't go above this limit. For those limits, it's in parts per trillion, I think, for mercury. Parts per trillion. Okay? With chemistry, when we're dealing with solution chemistry, we're dealing with things that are far more concentrated than parts per billion or parts per trillion. Far more. So there is a different unit that is used to refer to how concentrated something is, how much impurity is in here. First of all, where do most chemical reactions take place? Water. A watery environment. What unit do we use in chemistry? That unit is going to be called molarity. Molarity. Molarity is the moles of the impurity dissolved in the total solution. Now keep in mind that total solution is going to be a combination of the impurity and water. It's not just going to be water. Just like if I asked you to find the percentage of boys in this room, you wouldn't divide the number of boys by the number of girls. You would divide the number of boys by the number of girls and boys together. Right? So this is going to be the same thing. You will divide the number of moles, which is just a way of numbering things. Divide the number of moles by the total volume of the impurity and water. What is the symbol that we will use for molarity? Because I know you people, and molarity is too big a word to use constantly. Okay, how about this? How about if we use the symbol M? Big M, not little m, because little m would be meters. Big M. Big M. Okay, so knowing what big M stands for, let's solve some of these questions. You'll need your calculators. Get them out. You'll also need a periodic table. Get it out. Here we go. What is the molarity of 5 grams of NaCl in 200 milliliters of water? Step number 1, we need moles. We have grams. So what are we going to have to convert grams to? Can we? Yeah. This is what we learned to do on Monday and Tuesday. Grams is a normal number. Moles is a tiny number. So how do we make a normal number tiny? Divide. So what do we divide by? Do we divide by Avogadro's number? Or do we divide by the formula mass? So to find the moles in these questions, you need to divide by the formula mass. So Na is 23. Cl is 35.5. That's 58.5. So divide 5 by 58.5 grams per mole.
11.7 grams per mole.
How is that possible if you're dividing 5 by 55?
Okay.
I've got 0.85.
I got you. Yeah, I wrote this.
0.085? Is that right?
Yeah.
Okay, so notice that the grams cross out and you have a denominator in a denominator. What does your algebra teacher tell you about what happens to the denominator in a denominator? It becomes the numerator.
Yes.
It's some kind of reciprocal rule or something or other. I don't know. Okay, so we now have half of molarity. Molarity is moles moles divided by liters. Number 2, are we given liters? No. We're given milliliters. Can we convert milliliters to liters? You're going 3 spaces up. So it's jumps to the left. 200 becomes step number 3. Molarity is .085 divided by 0.200 is what?
0.425.
No, it's not much at all. Actually, it is. Most of the stuff you guys have played around with has been 0.1 concentration. Because we want there to be enough there, Ben, that it'll react, but we don't want there to be enough that it could possibly irritate your skin if it comes in contact with it. So it's not very concentrated. So if we were to make 0.425, that would be 4.25 times more concentrated than what we would be comfortable with. Oh. I thought you were making a very intelligent observation, noticing that 0.425 was pretty concentrated. Oh, I'm sorry, Ben. I misinterpreted. I implied that. Okay. All right. Because it's so much work, let's do it again.
Yay.
I love the click, click, click in the mornings. It sounds so beautiful. Can somebody confirm that? It's right? Huh. Okay, never mind. Don't. If Kelsey confirms it, it's confirmed. Gotcha. All right. Any questions before we do it again? Because Ben thought, hey, that's not that much work. I can do these all day long.
Yay.
Ben Walls. All right. I'll do this one quietly again. If you get stuck somewhere, look up, see what I'm doing. NaCl and C. Confirmed? Bam! Confirmed.
Yeah, I got 783. 783 continued.
That's funny because I think it's an iPhone issue versus TI. I mean, we've done the same thing. First period also had the same issue. They were using their TIs, I was using my iPhone, and we did the exact same thing, and they got .783 and I got .784. I don't know why.
You might need to skip
No,
over
I don't
this
think it's a
time.
rounding thing because we did the exact same thing. I don't know. No, iPhones are smarter. All right. Here we go. I'm going to teach you something that I wish my chemistry teacher in high school had taught me and that my chemistry professor in college had taught me because that would have helped me tremendously when I got to become a chemistry teacher and I didn't know how to do this. Okay? Before, I mean, these chemicals that you get in those bottles that you get to play around with, we make those. Eddie and I make those things. Okay? We add a certain amount of the solid into water. Now, truth be told, we could buy it if we wanted to, but that doesn't make any sense. Water is cheap. We can add our own water. So if they're needing 0.100 magnesium nitrate, we could buy 0.100 magnesium nitrate that the chemical company has made, or we can buy a bottle of magnesium nitrate solid, which we can make oodles of liters of magnesium nitrate, 0.100. You understand? So it's like buying when we buy orange juice, I never buy orange juice in a carton. I always buy orange juice in a can. Why? Because what have they done to the water in the can? I can buy orange juice in a can for $1.50, or I can buy orange juice in a bottle for what? Almost $4. You're paying $3 for what? Water. You can add your own water at home. So we get the can, we squeeze out plus it's kind of fun to eat the orange concentrate, isn't it? Have you ever had that? It's like sherbet. Yummy. Okay, so you squeeze out the orange concentrate, add your own water, bam! You got the same amount for 3 times less.
Is that a little frozen can?
Yeah, the little frozen cans.
No, I used to just talk about
So, instead of buying these solutions, we buy it in the solid form, and then we add our own water. Question is, in order to make a certain amount, which the recipes for a lot of these labs is a certain amount, how much solid do you add to how much water? So, it's as easy as 1, 2, 3. Step number 1, add up the molar mass again. Step number 2, multiply by the concentration. Step number 3, multiply by the liter version of the volume that you need. All right. We're going to do 3 examples, and we're done for the day. Adelante. Tienes que escribir más rápido.
He's saying mean things about us.
No, he's saying
I think
hurry
he's
up.
talking to Randy.
It's not Randy to hurry up.
I still didn't get
You
it.
understand the ring.
Qué mala onda.
I still didn't get it, senor.
No me importa. Vámonos. All right, here we go. Step number 1. Sodium hydroxide, which is NaOH, find the molar mass for it. So, plus NaOH, 23 plus 16 plus 1. .0 grams per mole, right? That's molar mass, the grams in a mole. Number 2, multiply. Multiply by what? Multiply by the concentration. 40.0 grams in a mole. Now I'm going to multiply it by the full version of molarity. Molarity is moles per liter. So notice that the liters cross out, giving you an answer in grams per liter. So 40 times 3 is the same as 4 times 3, but with a 0. Nope. It is just multiply. 120 grams per liter. Step number 3 is multiply. Multiply by what? Multiply by the liter version of this, which means you just have to move the decimal place. So 120 grams per liter times 0.200 liters. Notice that the liters cross out, giving you an answer in grams. Okay, that is not the answer. This is the answer. And it's very important that it be this. This is why I messed things up my first year in chemistry. This is why a lot of the experiments that I tried with my students didn't work. This is what I would do. I would come up with this number. I would get a graduated cylinder. I would add 200 milliliters of water to that graduated cylinder, and then I would add the 24 grams. What's wrong with that? That would give me more than 200 milliliters. Why? I was assuming that the solid that I was adding there had absolutely no volume, which was a stupid assumption. So then I really didn't have the concentration. I really didn't have 3 molar because I really didn't have 200 milliliters of it. I had more than 200 milliliters, which meant that the concentration was lower. What I should have done is I should have first added the solid down here at the bottom, and then add however much water gets me up to the 200 milliliter line. So then that would have been combined, the solid and the liquid together. That's what I screwed up. Yeah, but I learned. All right, let's do this again. It's as easy as plus times CuNO3 2. Kelsey, can I get an amen from you?
Amen.
No. I did it wrong? Oh, I did it right. Who else confirms that I did it right?
Amen.
All right. Kelsey, you let me down. You don't even have a calculator. Oh, yes, you do. You do have a calculator. You were hiding the calculator behind Bailey's head. Any questions on this one? Because Ben is about ready to fall asleep. So we got to keep going. Keep Ben awake. Keep Ben awake. All right, one more time. And then we're done for the day. This is as easy as 1, 2, 3, plus, multiply, multiply. Plus what? Plus the formula mass. So 137.3 or 137.1? What is barium?
137.3.
Because nitrate is a negative ion that doesn't react with anything. So it's always easiest to use nitrate. It's a good carrier pigeon. It's a good carrier molecule. Actually, particle. So if we want to bring barium to the party, bring it with nitrate. And if we want barium to react with something, then bring something like sodium with whatever you want it to react. Let's keep it chemistry over there. Spencer, confirmed?
Wait, why did you put 30?
What?
Put 300.
Because 3 milliliters is, most of my graduated cylinders are in milliliters instead of liters. It's just easier to go back to the original. I'm answering the question, the original question. The original question is how much would you make, how much mass would you need to make a 300 milliliter of a 2.5 molar solution? So the answer is 196 grams in enough water to make the 300 milliliters.